Hello students. Now we are going to discuss the solution of heat equation by the method of separation of variables. So here the heat equation means the flow of heat through the given material we expressed in the mathematical equation as a partial differential equation, that is dou u by dou t equal to c square into dou square u by dou x square, where c square is a constant. So this equation represents the flow of heat. Okay, and see the nature of this PDE here. This PDE is a homogeneous where u is the dependent variable, x and t are the independent variables, homogeneous and containing two independent variables. So as we discussed in the previous video, we find the solution of this heat equation by the method of separation of variables. Now, so as a independent variable is u, we first assume the solution as u equal to independent variables are small x and small t. So therefore we assume the product as capital X into capital T. Okay, this is the assumed solution. Now our work is to find the values of capital X and capital T. So here we find dou u by dou t. Okay, we differentiate u with respect to t, the small t. Okay, so this capital X is a function of small x, capital T is a function of small t. So when you're differentiating with respect to small t, so x is a constant, then differentiation of t is t dash, that is nothing but dou capital T divided by dou small t, that we represent as a t dash. Now we find the value of dou square u by dou x square, that is when we differentiate x two times, x double dash, that is dou square capital X by dou small x square, that we represented as x double dash, and t is a constant. Now we are going to substitute these two values in the given heat equation. Okay, when we substitute the values, x into t dash, okay, see dou u by dou t is x into t dash, right? Then c square dou square u by dou x square is x double dash t. Okay, now after substituting the values, we are going to separate the variable, that is the functions of x on one side, functions of t on other side. Okay, so x double dash divided by x, then t dash divided by t, and also I take the constant c square. Now the variables are separated. Now we are equating to a common constant k. Okay, then we taking the LHS equal to the constant, then RHS equal to constant. Now we are going to find the solution of these two ordinary differential equations. And also one more point you remember, we are converting here PDE to ODE. We are converting the ordinary partial differential equation to ordinary differential equation. Okay, so this is x double dash, taking x that side, that becomes minus x into k equal to 0. Similarly t dash minus t c square k equal to 0. Okay, so now, so this is what ordinary differential equations, d square x by d small x square minus kx equal to 0, and this is t dash, means this is d capital T divided by d small t minus t c square k equal to 0. So first we consider the first ordinary differential equation and we solve this. Okay, so writing this in the standard form, d square minus k, taking capital X as common, then the auxiliary equation is m square minus k equal to 0. So here we consider some different cases because we get m square equal to k. Okay, this k is not defined. As a k is not defined means that k may be, so as we consider a common constant, right? This common constant is what? It may be a negative, it may be a positive, because that we does not defined. So therefore here we are going to consider the different cases, taking once k as a positive, next k as a negative, then k equal to 0. Likewise we consider the different cases for k. So when k is positive, we take k positive in the form of p square, so that equation 2 becomes m square. We are taking k equal to p square, which is a positive. Therefore the values of m are plus or minus p. So these are real and different roots. For real and different roots, the solution is given by, so x is the dependent variable, the solution is given by capital X equal to c1 e to the power px, okay, plus c2 e to the power minus px. This is the one solution when k equal to, k is positive, k equal to p square. When k is negative, we take the negative in the form of minus p square, then equation 2 becomes m square minus minus plus p square, then the roots are plus or minus ip, which are real and which are complex roots. We got the complex roots. For the complex roots, we write the solution as x equal to, as we considered the arbitrary constant c1 and c2, we take the another arbitrary constant c3 and c4, c3 cos px plus c4 sin px for the complex roots. This is the second solution when k is negative. Now we consider the third case. So the third case is when k is 0. When k is 0, so that equation 2 becomes m square equal to 0. We wrote here 0 comma 0 because, so we have a equation of degree 2, so therefore we must have two roots. Okay, it is not simply m equal to 0, we have to write two roots 0 comma 0, which are real and equal roots. Two roots which are real and equal roots. For real and equal roots, we write the solution as x equal to another other arbitrary constant c5 plus c6 x into e to the power 0x. So this is the solution when k equal to 0. Likewise, for three different cases, we got the three different solutions for x. Okay, now we take the second ordinary differential equation, dt by d small t minus k c square into t. We write in the standard form d by dt as a capital D minus constants are k c square capital T as a common equal to 0. Okay, so auxiliary equation m capital D as a m minus k c square equal to 0. So again here also we consider the three different cases when k is a positive, when k is negative, when k equal to 0. Now when k is positive, so positive we take in the form of p square. So therefore equation 3 becomes m minus k as a p square into c square equal to 0. Therefore the roots are m equal to p square c square. This is a one real root. This is a one real root. For one real root, taking another arbitrary constant c7 e raised to c square p square t for one real root. This is the solution. Okay, now the second case when k is negative, the negative we take in the form of minus p square. Therefore equation 3 becomes m plus p square c square. Therefore the value of m is minus p square c square. So this is again a real, one real root. For one real root, the solution is given by c8 e to the power minus c square p square into t. This is the second solution. Then the third solution when k equal to 0. When k equal to 0, equation 3 becomes m equal to 0. So this is the only one real root again. So therefore the solution is capital T equal to c9 e raised to 0t. See that in this, for two different ordinary differential equations, three different solutions we got. Okay, now what we do, we are going to substitute the values of x and t. Okay, the assumed solution is u equal to x into t. Okay, first we substitute the value of x when k is positive, value of t when k is positive. This is the value of t, this is the value of x. This is the one solution. When k is negative, the value of x is here, the value of t is here. When k equal to 0, then this is the x value, this is the t value. Okay, so likewise for three different cases we got the three different solutions of u. Okay, so this u gives what? It gives the heat or the temperature of the material. Okay, this u gives the temperature of the material. Now for three different cases, what we are doing, see, of these three solutions we have to choose the solution which is consistent with the physical nature of the problem. As we are dealing with the problems on heat conduction, the solution must involve periodic functions. See, so the convenient solution for this heat equation is what we are considering, the solution must contain periodic function, because there is a flow of heat in the bar. Okay, when there is a flow of heat which is in terms of waves, when there are the waves we must have periodic functions. So therefore, out of the three solutions, the solution which containing periodic functions are what? Sine and cos functions. So therefore what we do, the convenient solution for this heat equation is equation 5. So therefore the solution is given by u equal to c3 cos px plus c4 sin px into c8 e to the power minus a square b square into t. So this is the convenient solution for heat equation. Thank you.